Okay, so here we are in our third lecture here on chapter 17. So we've talked about lipids in general, we've talked about the fatty acids, the saturated fatty acids, unsaturated fatty acids. We've mentioned the prostaglandins briefly last time, so now we're going to move forward into our discussion of lipids. In this lecture specifically, we're going to take a look at waxes and triacylglycerols and see how they differ from the prostaglandins and the plain old straight chain or kinked saturated or unsaturated hydrocarbons of the fatty acids that we've discussed so far. So waxes are esters actually, and they're esters of saturated fatty acids and long chain alcohols. So they each contain somewhere around 14 to 30 carbon atoms. So that's quite a large molecule here, especially compared to the fatty acids we talked about so far that were mainly 12 to 18 carbon atoms total. The beauty of these nice large waxes is that they provide coatings to help prevent loss of water from leaves and plants. We see here some bee activity making their beeswax. And again, the general structural feature is that ester bond separating the fatty acid, which brought the C double bond O OH group, and the long chain alcohol, which brought another OH group that condensed, spit out of water, and made this ester bond and left this large wax molecule behind. So here in table 17.2, we see some typical waxes. So beeswax, the wax that we saw those bees making in our previous slide, that's a 16 carbon fatty acid that condenses with a 30 carbon alcohol to give rise to that overall beeswax structure and a water molecule, obviously, as a result. Our source there is honeycomb, and the uses for beeswax, it's used in candles, shoe polish, wax paper, very useful natural product there. If we look at carnauba wax, now we have an even longer fatty acid, right? 26 carbon fatty acid, 30 carbon alcohol again. The main source here is Brazilian palm tree, and this is where you get your waxes for furniture, cars, floor waxes, shoe wax as well. Again, it's larger, so it's not so much the shoe polish we see in the beeswax, it's more of a shoe wax here. And jojoba wax is somewhere in between, right? It's a 20 carbon fatty acid, 20 carbon alcohol, and it's from the jojoba bush. And again, we see use in candles, soaps, cosmetics. That's a much smaller alcohol end, but an intermediate sort of carboxylic acid, the fatty acid end of things. So there's a few key typical waxes, and they're all obviously that ester functional group is common to all. Okay, so speaking of esters, the way we tend to encounter fats and oils, we don't see them as single fatty acids, right? They tend to be encountered as triacylglycerols. So they're triesters of glycerol, glycerol is the alcohol, and then those fatty acids that we talked about in the last lecture, produced by esterification, right? That's how we make an ester, and we eliminate a water as a result. And they form when the hydroxyl groups of the glycerol react with the carboxylic acid groups, the OH portion of that carboxyl group of the fatty acids. This is a major form of energy storage for animals, and we see our good friend there, the polar bear, needs a nice thick layer of insulation there under the fur to stay warm in those temperatures. So the animal fat underneath that fur is a nice insulator for animals like our polar bear friend that have to endure those temperatures. Humans, again, those of us who live in the Northeast anyway, still endure that every winter, although we probably store a little more fat than we need to for those winter time. All right, and here we see that the triacylglycerol forms. We have the glycerol itself, which is a 3-carbon triol, an alcohol, an OH group on each of the carbons. And then we have 3 fatty acids. In this case, they're all the same. They're 3 stearic acid molecules. They don't have to be all the same, but for simplicity, we had them all the same for this case. And then we make that ester bond and also a water for each ester bond that forms. So we end up with our triglycerol, in this case glyceryl tristearate or tristearin, a fat, and the 3 water molecules as byproducts. So this is our typical formation. Again, with this case we use specific fatty acid residues, but we could have changed those easily to make a different fat. All right, so despite what you saw on the previous slide, most naturally occurring fats and oils are mixed triacylglycerols. So they all contain that glycerol, but the ester bonds are linked to 2 or 3 different fatty acids instead of all the same. Typically, we see palmitic acid, linoleic acid, stearic acid as the primary fatty acids that are involved in those triacylglycerols. So we see here a possible structure of a mixed triacylglycerol. So it's got a stearic acid residue, an oleic acid residue, and a palmitic acid residue. So we've got 2 of those 3 typical ones, right? We don't have any linoleic, but we do have an oleic, which is a common one, as we said, for the fat from olives. Olive oil is rich in oleic acid residues. Okay, so let's see how close attention you've been paying. In this learning check, you're asked what are the fatty acids in the following triacylglycerol. Now, there's a couple that you're going to be familiar with. We've seen them quite a bit, stearic acid in particular. We've seen a fair bit. It's our principal saturated fatty acid, so I think that one you should be able to pick out. We've also talked a lot about oleic acid, but again, that last one there, the lowest numbered one, maybe you'll catch it, maybe not. Again, I try not to do a whole lot of memorization here in the course, so if you just can't remember its name, but you can recognize it as a saturated fatty acid, for instance, then you're in a pretty good place here. But let's see how you do. Go ahead, stop at the video here, try to come up with those names, and we'll check your work on the next slide. Good luck. All right, so I sort of gave it away, right, with the stearic acid and the oleic acid, and hopefully you've seen at least stearic acid enough now that you're getting used to it, because it is one that comes up again and again, and it's one you should probably have committed to memory. Oleic acid, because it has that nice middle carbon-carbon double bond, it's a popular mono unsaturated fatty acid. That's another one hopefully that you could recognize. In our last one, myristic acid, it's a little bit more unusual of a name. It's a little bit less common of a structure, so if that one escaped you, it's not a big deal. But if you're not sure what any of these are, or what's going on, or how we're making these triacylglycerols, then certainly it's time to get in touch. But if you missed that last one, it's not a big deal here, and I try not to do much memorization here on the exam with our particular names of our different fatty acids. Let's do one more learning check before we move forward. In this one, you're going to draw the condensed structural formula for glyceryl tripalmitolate, or tripalmitolene, if you want to use its common name. And what that means is, of course, we're going to have 3 palmitic acid residues. So if you need to look up palmitic acid, that's fine. That's not one that we said you had to commit to memory just yet. So far, stearic and oleic acid we've seen a lot, and hopefully you have memorized. But if you need to flip back and see what that palmitic acid looks like, go ahead, do so. The main thing here is that you be able to show that product, that glycerol plus 3 palmitic acids, giving rise to this final product. So stop the video here, draw your final product, and start it back up to check your work. Good luck. Okay, so there it is, right? The palmitic acid itself is a, what is it, 16 carbon total, right? With a carbon-carbon double bond between carbons 9 and 10. And we just need to show that 3 times because we had the tripalmitoleate, and there we have the ester bond between the glycerol and the fatty acid. So we kicked out of water from each of those glycerol fatty acid bonds to make those 3 esters. So there it is. Hopefully it's the same thing that you have written down on your paper, and we're in good shape. If there's a problem. Again, if you had to look up that palmitic acid is a 16 carbon with a 9-10 double bond, that was fine. But if you're really not sure how to turn that into a triacylglycerol, then we should probably get in touch, and I can give you some guidance there. Otherwise, let's move forward. Okay, so we have some general trends here for melting points of fats and oils. Again, of course, it's not always cut and dried. There's going to be some cases where we buck the trend, but for the most part, a triacylglycerol that's usually called a fat is a solid at room temperature. This is prevalent in meats, whole milk, butter, and cheese. This is where you tend to see the fats, the solids at room temperature. If we have instead a triacylglycerol that's called an oil, it's usually liquid at room temperature, and it's prevalent in plants such as olive and safflower oils. The exceptions here would be things like palm oil and coconut oil, which we call oils, although they are basically solids at room temperature and pressure, right? So they're, greasy solids, but they're solids nonetheless. And so you have to be careful there with a couple of the oils, particularly coconut and palm, that have lots of saturated fatty acid residues, tend to be more like the animal fats, although we still call them oils. So fats tend to come from animal sources, oils tend to come from plant sources, and we even apply that oil name when it's a plant source that gives us a solid at room temperature. So the reason the oils tend to be liquids at room temperature and pressure is they tend to have more unsaturated fats. So the plants tend to have more unsaturated fatty acids that they make into their triacylglycerols. That's also the case that they have more cis double bonds, causing those kinks. When you have the more unsaturated fats, you have more of those cis double bond kinks, and you can't therefore pack those triacylglycerol molecules as closely together as in the more saturated animal fats. So they tend to have the lower melting points than do the saturated fats, and therefore they tend to be liquids at room temperature and pressure, with the notable exceptions of coconut and palm oils. Here we see one of my favorite triacylglycerols. This is an olive oil typical molecule, glyceryl trioleate or triolein, 3 oleic acid residues that have formed this ester linkage with glycerol. And as a result, we see, because the oleic acid itself has a carbon-carbon double bond between carbons 9 and 10 of the fatty acid chain, we can't pack it very tightly. It's got the kinks, and those kinks don't allow for the close packing that a straight chain like a stearic acid residue would allow for. So as a result, we can't have the significant, or at least not as significant, dispersion forces as you can in the case of a stearic acid residue, and you get an oil, a liquid at room temperature and pressure, as opposed to a solid fat from an animal source typically. Now, the big misconception that might be out there is that the animal fats have all saturated residues, and the vegetable oils have all unsaturated residues. That's not true. We see here, even in solids like beef tallow and butter, you have some number of polyunsaturated, monounsaturated, and saturated fatty acids present. It's just a matter of having more of the saturated and fewer of the polyunsaturated or monounsaturated fats in the animal sources than in most plant sources. But if we look at that coconut oil, my goodness, look at all those saturated fats that we have there. That's why coconuts probably aren't the best thing for us, although some of us enjoy them. Coconut's one of my favorites, but it's not very good for you. It's got a lot of saturated fat. It's pretty stable as a result. Not a whole lot of chemistry you can do with all those saturated fatty residues, but certainly not a health food if you're over consuming because of all those saturated fatty acid residues. And then if we look, we see with the plant sources, we tend to have lots of monounsaturated for olive oil, and then canola oil has a fair deal of monounsaturated, but more of the polyunsaturated than in the case of olive oil. If you go down to things like safflower, you've got very large amounts of polyunsaturated and relatively little mono or saturated fatty acids. So depending on what the research is at the moment, I think still we're looking at the oils like olive oil with a very high monounsaturated fatty acid content as being sort of the healthiest option. But again, probably a varied diet from these different natural sources is the best thing in the long term.